Hello everyone, my name is Shaneel and I'm here to present to you my Shaneel451 thesis which I have completed this semester. The topic for my thesis is active filter design and compensator analysis using non-active power theory. So, in today's world, the number of non-linear loads that are being used on the power systems has significantly increased in comparison to olden days. Some of the examples of these non-linear loads, which is at domestic levels as well as in industries. At domestic levels, some of the examples of these non-linear loads are fax machines, UPS, uninterrupted power supply, computers, and fax machines, printers, photocopiers, and in industrial levels, it's the compressors, fans, and pumps. So due to these non-linear loads, when it draws power from the utility, obviously when there is power, there is voltage and there is current. So when this current gets transferred or supplied from the source, it consists of a lot of disturbances. These disturbances are in the form of harmonics. The damaging of harmonic currents and the effect on the electrical distribution system has grown heaps in the recent years. So these harmonics, because of these nonlinear loads, it gives rise to the harmonics. And these harmonics, it causes issues in the system. Some of the issues these harmonics cause are unbalanced voltage, it causes overheating of equipment, it causes electronic protective device malfunctions, as well as it causes low power factor. As power engineers, our role is to reduce these issues so that we are able to achieve or get maximum output at the load end. So the ways we can reduce these issues are by using methods such as active filtering, passive filtering, or hybrid filtering. In passive filtering, it uses passive components such as inductors, such as capacitors, and in active filtering is where we have an external design from which it producing compensating current, so that the compensating currents are put into the system and reduce the non-active component of the current so that the real current gets supplied to the load. There is a note in here: eliminating harmonics at their source has been shown to be more effective method to reduce harmonic losses in the power system, which means that reducing the harmonics at the supply end is beneficial compared to reducing it at the load. In order for us to understand this mitigation technique, it's important for us to understand the non-active power theory behind it. In this non-active power theory, it uses time-based instantaneous components of power, which was derived by Fraser in 1930s. However, the current that gets transferred from the supply, it consists of two components, that is non-active, instantaneous non-active current and instantaneous active current. What we want to achieve is to get active current from the supply to the load. And the way we can achieve that is by using active filtering. The active current equation is given by average power divided by voltage RMS squared times the reference voltage. This reference voltage that is shown there is the supply voltage, whereas the non-active instantaneous current is given by the main current, supply current. Removing the active component gives you the non-active component. Now let's look at the method that I've used to mitigate these harmonics is active filter. Active filter, the main part of active filtering it consists of an inverter as well as a hysteresis current control method. In the inverter, it is made up of 4 diodes, which is configured in a H-bridge design or H-bridge configuration. And the power source, the way this inverter gets its power, it's from a DC battery. I'll show you, okay. This is the diagram of the diagram I implemented on MATLAB, which is of an inverter. These are the 4 diodes, and this is a battery source. This battery source, sometimes we use capacitors as it is an energy storing device. However, for using capacitors, it needs an initial value. So more convenient way of implementing on MATLAB is by using a DC battery. However, when this inverter gets connected to the main system for the compensating currents, it uses an inductor. This inductor is used to reduce the ripple in the compensating current as well as to reduce the voltage. The switching of these inverters, the switching component comes from the hysteresis current control method. The hysteresis current control method compares the current from the main supply and the active current from the main system. It compares those current, it goes through the hysteresis relay, and the output has got it has got 2 outputs, and those 2 outputs are used as the switching gates for these diodes. So when it outputs 1, that will mean the diode 1 and 2 are operating, are on, where these 2 are off. When it outputs 0, will mean this, it goes through a NOT gate, which means the output is 1, causing this to be on and this to be off. That's how the control method, the hysteresis control method, works. Here it shows a diagram which I have implemented on MATLAB as to how I have tested my active filter compensator on a load which was a uncontrolled bridge rectifier consisting of diodes with an RL load. When this was implemented on MATLAB, without the compensator, the current supply and the load current, the waveforms were exactly the same because it was in series. However, when the compensator was connected, the supply current was turned into sinusoidal and the load current remained the same. We were able to compensate the supply current by compensating the non-active current by injecting the compensating current into the system. Another test was carried out on a controlled bridge converter, whereby the diodes got replaced by thyristors, and these thyristors, since you are aware, these thyristors are fired at different angles, yes, and they can be forced turn on, but you cannot turn off. However, when using the thyristors as the load, this was the load current waveform, whereas this is the supply current waveform. As you can see in the supply current waveform, it's not a pure sinusoidal. The reason being because the system consists of inductors, and due to this LDIDT effect, we do have these spikes on the waveform, whereby the current in the inductors, as you are aware, cannot be changed instantaneously. Hence, we do have those decay period, those waiting time for those currents to decay from the inductors. That's the reason we have got spike. But, however, the supply current is still very much a sinusoidal. We were able to achieve we were able to remove most of those high harmonics. In conclusion, I wish to mention that the instantaneous power theory is an appropriate field of study for active filter implementation. It has made the results achievable through time-based measurement compensator control system. The total harmonic distortions which were measured on MATLAB, it did show without the compensator the percentage level of harmonics was about 20 to 30%. However, after active filter was connected, these non-active components got compensated. The total harmonic distortion was reduced to about 0.2 to 2%, which is still within the range of IEEE requirements, which is less than 3%. So using active filter is a better mean, or is a good means of reducing these harmonics in the system. With this, I'd like to thank everyone for listening to my presentation, and I hope it has been of some help and educational as well. Thank you.